Hello guys, welcome to the heat and mass transfer class. So today is week 4 steady state conductions. So today we're going to be talking about slightly more challenging stuff, which is extended surface remaining under the steady state conditions. Okay, so let's go into it. So let's recap the last week. From week 2, we derived energy equation, and we always use these equations, right? And then last 2 weeks, we learned steady state condition, which is not all the temperature is not changing depending on the temperature times. So this is supposed to equal 0. There's no internal generation this week, no dissipation function. So we eventually got the Laplacian equation as like this. And then last week we learned the one-dimensional conduction, and we expressed this equation as like this, right? So based on these equations, so we derive various types of temperature distributions and heat flux Q depending on the geometry. So, for example, plane and cylinder and spherical. So yeah, so I believe all you guys understand how this distribution and heat flux works. Okay. But today's thing is slightly different. So today we're going to be talking about the extended surface. The purpose of why we have to study the extended surface. The extended surface is, we use this because we want to increase heat energy transfer. Between the surface and neighboring fluid. So the background fluid, right? So to realize this, so we usually utilize the extended surface using the fins or spins, something like that. Okay, so let's look at this figure. So in this situation, there is initial surface at x equals 0, right? But we added the extended surface like this, having the area like this. This area is defined as a cross section of extended surface, and this Sx is all the surface area comprising the Ax, this area plus this thing as well. So in these situations, we can define that there might be the heat flux from the original surface via conductions, and we call this Q1, and this Q1 will pass through our control volumes, and Q2 will be here, right? And during the conduction, there might be the convection as well in this surface, right? Yeah, so we have to consider the Q1, Q2, Q3, everything. So in this situation, we also studied under steady state condition. Yes, so there's nothing change in heat flux depending on the time. Okay. All right. So now we're gonna make the energy balance equation. The energy balance equation is very easy, right? So we define the Q1, the Q2, Q3. There's no energy loss in here, so we can calculate the heat flow rate like this Q1 equals Q2 plus Q3, and this Q1, Q2 is relating, Q1, Q2 is related to the conduction, right? And this Q3 is supposed to be a convection term. Yeah. And now by using this energy equation, now we can make equations because we learned this, right? This very makes sense. The Q1, oh no, sorry, this is Q1. Q1 is here, right? Q1 is the Ka, the temperature with respect to the x at x equal x. The position is x. But after the x plus delta x in here, this area, so we shall express the Q2 as like this, and the convection is expressed as like this, right? Okay, so this is Q2, this is Q1, and this is the Q3. All right. So from these equations, so we shall divide this equation to delta x, and we will get this equation, right? Right. And this p value, the perimeter, which is the surface area divided by delta x, right? So we call this 둘레, right? 둘레라고 하죠. Okay. So by using these equations, this one, so we now do the delta x goes to 0, then we can easily make this part more simple, like x ka dt over dx, right? So the final equations can go like that. Right? Yeah. This is the equation, general equation that we have interested. Okay. So all the equation will start from this equation. Okay. So now we are gonna move to some specified geometry. This is one of the example of the extended surface, which is fin or spins of uniform cross sections. Yeah, these are the geometry. And the uniform cross sections, what is the meaning of uniform cross section? Which means that the area of extended surface are not changed depending on the s values, which means as can be the constant a, the ps can be the constant p. Okay, and if we assume that k, all the coefficients are constant, then from these equations we can take out this value from out and can divide by this value in all the equations, then we can get this equations. Yeah. Now this is a special equation for the fins or spins of uniform cross sections. Okay. So once you find this kind of conditions, you can start the differential equation from here. Okay. All right. And this is the next example, the straight surface with linearly varying cross section. So in these situations, the surface, I mean area and perimeter can be varied depending on the x values, right? So we define this is A0 where x is 0, and this can be the AL, right? And then we want to calculate some area A depending on the x, right? But this is very simple, which means, for example, so A x minus A0 over AL minus A0 can be the x over L. So we can easily make this equation, right? So if we solve these things depending on the AX, then we can get these equations, right? So the area at X point can be calculated like this. So the perimeter is also is exactly same equations. So you can derive by your own, by yourself. You can derive by yourself in your home, okay? All right, so in these cases, once you found the straight surface with linearly varying cross-section, then you should add the area factor like this, and now the area is a function of the x value, right? So it can be changed. Okay. So not only this circular stuff, let's also derive this kind of the rectangular stuff. Okay. For this rectangular stuff, we can define the A0. If we assume that this value is T0 and T0L, and then we define this as W width, then we can define the A0, the overall area can be calculated as 2T0 multiplied by W, right? How about AL? AL can be calculated like this. This is TL, so 2TL multiplied by W, because these W values are not changed depending on the X value, right? So we can define AL like this. How about P0? P0 is very simple. So P0 is the length of this sum of all these, right? So 2T0 plus W multiplied by 2, right? And how about this? These are also same, 2TL plus W, and also 2TL and W. So we will get these equations, right? Alright. So our previous equation was with respect to the x minus HP over Ka T minus T infinity equals 0, right? And what was that? A0 minus A0 minus AL x over L, and P's are same, right? So by adding this equation into our original equation here, then we can derive these equations. Okay? So we add, okay, let's just write down the P as well. P equals P0 minus P0 minus PL x over L. Okay, let's just substitute this to here, and please multiply by A. Then we can see this part in here, and this part here, and this P part in here. Okay. not too much difficult. All right. So the equation goes slightly more difficult when the surface areas surface areas are changed depending on the x, right? But you don't have to memorize everything, all these equations. You just try to understand this and this, and just try to understand these equations. Probably you shouldn't memorize these equations, and then you can substitute these things and these things, right? And in the problem, I think these conditions shall be more easier than these equations. Okay, and here comes the last part, the curved surface of uniform thickness. All right. In this situation, there are curved surface, so we shall use the the radius r, and a can be defined like this: 4 pi r t. The p we should divide by t, right? So 4 pi r, so which makes sense. The r is here this r0, and here this rl, right? So extended surface is this one, okay? Not this. Don't confuse. Okay, this is also very simple. So we derive the overall equations as we discussed in previous slide. The dt over dx minus hp t minus t infinity is 0, right? We learned this. Yeah. But this is not a one-dimensional, right? Not a function of x. This is the function of r, right? So we shall add change like this. What is k? 4 pi rt dt over dr minus hp t minus t infinity equals 0, right? Yeah. So after we calculate this, so we will get these equations, okay? So yeah, the second part and first order part and this part. Okay. Oh, sorry. You should substitute this 4 pi r to here, okay? All right. So yeah. So we call this Bessel's equation. Of zeros order, okay? And we assume that k and h are constants in here, but the other equation can be way more difficult when the k and h values is changed depending on some conditions, okay? Right, but you don't have to remember the name of this equation. Just try to derive the proper equation from the start equations, okay? Yeah. Okay. Right, this is part 1, and the next record, so we're gonna actually solve these, temperature profile equations, and we'll get the solution, okay? Good. All right, so let's move to the next. Okay. So yes, we got a solution for the temperature profile like this, right? And now is the time to solve this problem. Okay, so for these cases we assume that this is the straight fin with constant cross sections. Yes, for these conditions, we can say that this HP over KA can be a constant. So we define these things as m squared, and then we change this t minus t infinity as a theta. So we tried this before once, right? So the equation can change to the sorry. Oops. Minus m squared equal 0, right? So therefore, from this equation, we can make a general solution to these equations, like this and this, that is C1 EMS e to the ms plus C2 e to the minus ms, or this sentence. So we need to find what is C1 and C2 and what is A and what is B. Yeah. To fully get these variations, we have to, set up the boundary conditions, right? So boundary conditions. So let's imagine the structure, and then we can imagine the three setup boundary conditions. Now from this time we assume the three situations, okay? And we'll solve the equation at each condition for sure. So oops. Three set of boundary conditions. Okay, the first thing is, let's say set A. Okay, for set A, we decide that T is equal to T0 at x equals 0. Okay, here x equals 0, x equals L, right? And T must be the TL at x equal, what is that? L, right? We can make these boundary conditions when there is a temperature known at x equal L, right? Okay. But we also can make the other boundary condition, which is all the first boundary condition is supposed to be same, right? T equals T0 at x equals 0. But in this case, we shall make condition like dt over dx equals 0, which is temperature gradient is 0 at x equal L. In here, the temperature gradient is 0. T gradient okay. For third case, let's say set C. Okay, for third case, the first condition is also same. T equals T0 at x equal 0. Second is minus K dt with respect to x equal h t minus t infinity. What does that mean? The conduction rate is equal to the convection rate at this point. So at equal L, right? So in drawing, this is the end of the fin, and there might be the conduction. It flows like this, and then after it arrives here, it will be out as a convection, right? At this rate, at this point, they're same, right? So you can make a boundary condition depending on the conditions, what they suggest in the questions. So here is the thing that we can try, okay? Yeah, but in this solution, we will use all these three boundary conditions at each cases, okay? So you should remember these boundary conditions before we go to the next slide. Okay. So now we try to solve the problem. So this is the final solution, and final solution for the first set of boundary conditions. So what was the first boundary conditions? You guys remember? When x equals 0, t equals t0. When x is L, t becomes t L. Right? And we assume that theta is t minus t infinity, and m squared is h perimeter divided by k area, which is constant, right? The solutions that we have to solve was theta was c1e minus e to the mx plus c2e minus mx. So by substituting this boundary condition in here, we will get these values. Okay? You can do that. I will not solve the problems because it's too much mathematics inside. Okay? So there's one more thing that we have to do is, which is L goes to infinity. So when the L goes to infinity, so let's say that in this part, this partial goes to 0. So these guys goes to 0. So eventually all this stuff will go to 0. So the theta over theta 0 will be the e to the minus mx. Okay? This solution can work when the L goes to infinity. What does that mean? The fin is very, very long. Alright, this is a solution for first boundary conditions. And also we can obtain the other concept by using the other set of boundary conditions. For example, so we got this, right? And then this is the second boundary conditions. When t equals t0, x equals 0. In these cases, gradient t was 0 at x equals L. Right? Then we can get these values, either these values and these values. Okay. Right. especially for these cases, if L goes to infinity, this theta over theta 0 also goes to e to the minus x, which is exactly same with the previous slides. Okay, so it's a long. If you have a long fin, long fin, it means that the boundary condition 1 and boundary condition 2 goes to the same conditions. Okay, think about that, the physical meaning of this boundary condition. Okay, and also let's try the set C of boundary conditions. Okay, but what's the set C? Set C was the same for first boundary conditions, but second one is conductions and convections are exactly same at f equal L, right? Then you can obtain this value. Okay. Okay. If you have a time, please try to solve this problem. Okay. But I would say this is not 100% important, but just please keep in mind the overall flow. Okay. Let's see. And for these equations, we can make it simple. First thing is if t equals to infinity and L equals to infinity, then also this equation is same as the result that we got in the previous slide. Okay, or if we d theta over dx equals 0 and also L goes to infinity, then we will get this term goes 0, this term goes 0, so we will get this value, which is exactly same with this one. Okay, this looks quite confused because at some conditions the solutions are same, which means is that if L goes to infinity and if there is some under some conditions, all the situation can be same, right? But you don't have to memorize this, the equation, but this is kind of homework that you guys must think why the solutions can be same, can be exactly same in some condition, under some conditions, specific conditions. Okay, yeah, these are the very important. Yeah, solve the differential equation is not important in this class. We must understand the exactly physical meanings of those, and we can solve the problem. Okay, all right. So so far we have studied the T distributions, right? But from now on we will solve the heat flux, heat transfer, right? So let's just think about that. There is a surface and there is a fin like this, right? Then the total heat transfer can be considered as two stuff. The first thing is the integral of convection heat transfer expressed over the surface. How can you draw this? Like this. In this surface, all these surface, there might be the convection, right? And after we integration all of those convections, then we shall get the heat transfer, right? The second part is the energy conduction into the extended surface at base. It means that in this base heat must be transferred through the conductions, right? So this explains the overall heat transfer rate at x equals 0. And because this is the conductions, we can express the conduction heat transfer rate like this, which is already studied before. Okay, so you can use either this equation to solve to get a Q values, Q equations, but it seems that this one looks slightly, easier, right? Familiar with us, because we use this equation very long time. All right, here's the T distributions. That we got, right? What was that? Using the set A boundary conditions, right? You don't need to remember the boundary condition. I will let you know. So the Q is minus K over dt, K dt over dx at x equals 0, and the boundary conditions, set A boundary condition was like this. So after solve these equations, we will get this. Okay? But look at this equation. So we can make the one more equation, which is when L goes to infinities, how does it change? These guys will be cancelled, right? So our final Q value can be a Ka and theta 0. Okay? And theta 0 is theta 0, T0 minus T infinity, and K, A, M's are constant that we derived in the previous slide. Okay? Alright. The next thing is the boundary conditions. Set B boundary condition and set C boundary condition. Okay, and we already got these values from the above slides, right? And also by using these equations, we eventually get this. I will not solve all of those guys, okay? Because those are not important. Just remind the flow. All right. So this is the last slide for today. Yes. So from this one, we can define the one thing, which is fin efficiency. So fin efficiency is actual heat transfer from extended surface divided by the maximum possible heat transfer from extended surface, which means in ideal cases, all the actual heat transfer from extended surface can be the maximum possible heat transfer, right? There's no loss. But in actual fin, there might be the transfer loss, right? So that's the fin efficiency, okay? Right, so we can derive this equation like this. The overall heat flux, Q total, can be the sum of the primary surface heat flux of primary surface plus heat flux of fin. So this does mean that, let's say, here is the main body, and here this is the extended surface, right? So there might be the heat. There also might be the heat transfer. I mean, heat goes out to the neighboring fluid. This is the Q primary surface, right? And this, so all the convection occurring in the fin is a Q fin, okay? So all the heat flux can be expressed by the sum of the Q primary surface and Q fin. So we change to the convection's equation like this. So A0H T0 minus T infinity. Yeah, here there is T0, right? And for here, the AF T minus T0, we don't know T. We don't know A. But there is a, yeah. So we can express like that, right? So these are the portion of actual heat transfer from fin, right? Good. So we will add the fin efficiency, right? For fin, the transfer rate is not perfect, so we will modify the efficiency term in here, right? And this is a true efficiency of the fin of heat transfer, right? Yes. So we can take out the H from out here and from out here, so the final equations can be here. Alright, so Q total is H and A0 plus AF, efficiency, and T minus T0. This is Q total, which we can expect it from the surface having an extended surface like this. Okay? Okay, oh, sorry, I want to make sure the definition of the variation, which is A0 and AF. A0 is exposed area. Of this primary surface, okay? What is AF? Total surface area of fin, right? Right, okay. So this graph exhibits example of the fin efficiency depending on the, yes, these values RL over R0, which means what is the ratio of this RL on R0 is like this. And HK, these values are usually, the constants, right? Yeah, and we assume that T is very, very small, right? Very thin extended surface. The efficiency is depending on the ratio of the radius, okay? Right. So it is very clear that if everything's are same, the efficiency tends to go down, right? As the RL, R0 increase. Which means that as the fin is longer, their fin efficiency tends to go decreasing, right? Tend to go lower value, right? Because think about that. So how can you maximize the efficiency? Think about that. The heat transfer can be maximized when the temperature of extended surface equal base temperature. What's base temperature? T0. But let's say if these extended surfaces are very long, it's really hard to keep these conditions, right? So it's really hard to maximize the heat transfer from the primary surface to the extended surface, which means that the fin efficiencies can be decreased. Okay? Right. Okay. So here's the last slide that we wanted to deal with for today. And there is two problems for you, the backside. So you can, I think you can solve these two problems by today, and also I will upload it how I solve this problem. Okay. So in the rest of time for today, please try to solve this problem, and then check it out later after I uploaded the solution of this problem later. Okay. Good. Good. Okay. So let's recap. So today we learned the steady state conductions at the extended surface, right? So, and we derived the T distribution for sure, and then heat flux Qs for sure as well. And finally, we also defined what is the fin efficiency, right? So all the solutions of T distribution and Q value was slightly challenged in terms of the differential equation, right? Now, all the physics are very simple. All the geometries are simple, but the mathematics is kind of difficult, right? So if you have a time to solve this problem, you can do that. But I would say that if you see the problem set in the outside, in the backside, you don't need this kind of equations. Okay, you can just solve the problem. Okay, if you think that you need some equations, then you can just copy it from this slide that we learned today. Okay, it's okay. Good. So it was so fun, and this was the first recorded classes. So okay, good. I hope everything is okay. Okay, and see you on Wednesday. And on the Wednesday we will study not the one dimension, but the multi-dimensions steady state conductions, and we will drive the T distributions and also heat flux in a 2- and 3-dimensional systems. Okay. Oh yeah, it sounds very difficult, right? All right, guys. This is end of class, and thank you for listening.